Hi, I'm Kellon. I'm in the Simling Lab here at the Loftus Center. How many of you have taken medications before in your lifetime, right? Everybody, right? It's sort of like a silly question in a sense. It's a very commonplace in our society. So when you take a drug molecule, right, you have a headache, you take a pill, you inject that pill contains small molecules. Those small molecules have to traverse through your cell in order to find its drug target, right? Once it finds the drug target, it then binds to that drug target. But in order for it to pass through the crowded cell, it needs to move around a bit. It needs to change its conformation, change its shape. So for example, if you look at this particular protein here, this is a receptor that's used for pain relief. And in dark blue here is a drug that actually binds this receptor. Once the drug binds to this receptor, it changes this alpha helix shape to a different structure. And then if you look carefully at it, this particular alpha helix contains two dihedrals known as phi and psi. Now the change in those dihedrals will actually change the conformation. And understanding how those dihedrals change, we can be able to study the dynamics and the motion, such as the video that Lawrence showed earlier on. And our textbook classic example is looking at butane. So in any organic chemistry textbook, you learn about the different conformation of butane. So butane changes its dihedral, which is shown on the x-axis, and as the dihedral changes, the energy also changes as well. Now, to calculate this kind of conformational changes, we normally use an advanced method known as quantum mechanics. Unfortunately, we cannot use quantum mechanics on large systems such as proteins and DNA. So if you want to understand proteins and DNA and we want to look at the rotational bonds in the proteins and the DNA, we need to come up with a better idea. So what we do in our lab is we use molecular mechanics. And then we use a particular set of cosine functions to be able to reproduce the quantum mechanics energy profile. And this is what a cosine function looks like. And within that cosine function, we have to be able to obtain what the height of the cosine is, what the periodicity of the cosine is, what the phase shifts in the cosine is, and how many cosines we're going to use so that we can reproduce the QM energy here. And we do this all on graphics processing units. So the same GPUs I use to play your video games, such as Call of Duty, which is one of my favorites, we do all that on GPUs. So if you want to know how we use GPUs in order to parallelize the parameterization of dihedral parameters, you can come see me at my poster all the way in the back in the research section. Thank you.